Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and this episode is about detecting earthquakes early and how that can make a difference in saving lives. The issue is that earthquakes seem to arrive without warning. One moment, everything's normal, and the next, the ground is moving, buildings are falling over, chandeliers are falling from the ceiling, and this creates the impression that earthquakes are unpredictable, that there are these random events that happen, and that we can't do anything to stop them, to detect them before they happen. In reality, there are physical signals under the ground that are traveling before the earthquake actually hits, giving us an opportunity to do something. The challenge is that these signals come very, very soon before the earthquake, meaning that it's very difficult to detect the signals fast enough to actually matter. So before all this starts, we need to get an impression of what an earthquake actually is. The Earth's crust is broken into large tectonic plates, basically huge slabs of rock that make up the Earth's surface. These plates are moving slowly over time, and sometimes they run into each other, and friction causes them to lock together. As they continue moving, this friction gets higher and higher, creating stress. Eventually, on these borders between each plate, called faults, stress builds up too much, and the friction is overcome, and they move. When stress exceeds the friction, the fault slips suddenly. The stored energy, with these plates pushing and pushing against each other, is released, and that's what causes earthquakes. When earthquakes happen, they release two types of seismic waves. The most important are P waves and S waves. P waves are called compressional waves. They push and pull rock in the direction that they're traveling in. They move very fast, and they arrive first, before the S waves. The S waves are the dangerous waves. They move the rock side to side, called longitudinal waves. They travel much more slowly, but they cause the damage of the earthquake. The time gap between the P waves that arrive first and the S waves that actually are the problem is crucial, and what makes there an opportunity for us to detect the waves and do something about them before the earthquake actually hits, and we have significant issues. Unfortunately, this gap between the P waves and the S waves is only a few seconds. Fortunately, the farther you are from the epicenter, the place where the fault lines move, the longer the gap and the more time you have to react. Even a few seconds here can be very valuable. One confusion people have is between earthquake prediction and early warning. Prediction means knowing something days, hours, years in advance, but this is currently not possible. Fault systems and the interaction between these tectonic plates is very complex and chaotic. Stress buildup is almost impossible to observe from the surface, but early warning is different. That's what we're looking into. It means detecting an earthquake after it starts, but before it hits you. This distinction is crucial because it allows us to know what we're really able to do. So, how do we detect these earthquakes? Well, technology called seismometers are what we've done in the past. They are the oldest earthquake sensors, and what they are is a mass supported by springs, hanging down from springs. When the ground moves, the support system for the mass also moves because it's connected to the ground. It shakes a little bit, and therefore, the mass, which stays in the same place because of inertia, will not move. Thus, the support system is moving relative to the mass, and this is what a seismometer measures. This relative motion is recorded and used to detect the existence and magnitude of earthquakes, regardless of size. Modern seismometers are so sensitive that they can detect motions smaller than a nanometer. Networks of seismometers can triangulate the location and the epicenter of earthquakes based on magnitude of these relative motion at different places. However, these seismometers must be very close to faults to be effective. even miles away, these nanometers are all that you're measuring. Something that is very, very small can be very hard to measure. Additionally, they're subjected to interference from noise, like traffic, installation and maintenance, and other things. Additionally, creating these and making these very, very sensitive machines can be expensive, can be hard, and they can be limited to very specific locations. Therefore, it's not easy to get these across the globe. In lower income places or places with less people, you won't be able to install these seismometers. And therefore, information about where these earthquakes are occurring, who they're occurring to, and what the impacts are is limited. This motivates an exploration to find new sensing approaches that'll be able to detect these P waves faster so that we can solve the problems without expensive, clunky, and frankly ineffective earthquake sensing systems. These early warning systems are measuring the P waves, like we said before. Software can feel the ground and measure the wave speed and the amplitude. This allows algorithms to estimate location and the magnitude of earthquakes. This can issue alerts in communication systems before S waves arrive and before real problems occur. Fortunately, these systems that are measuring the P waves already exist. They allow things to stop trains immediately, to pause surgeries mid-surgery, shut down gas lines, open elevator doors, and allow people time to take cover and take shelter so that some activities might not destroy things, break things, or even lose lives. This idea of silent sensors is very important. Not all the earthquake signals are vibrations, and these changes are happening before strong motion and problems occur. And while these signals are subtle, physics allows us to sense them. Another way that we can sense these P waves before the S waves come is in electrical signals from this stressed rock on the ground. Certain types of rocks, generate electrical signals when they're under stress. Quartz-rich rocks exhibit piezoelectric effects, meaning that when they're squished or pulled, they have an electrical charge. This stress moves charges inside the rock, meaning that we can detect this movement, detect this change in charge, and detect when an earthquake is coming. These signals are extremely weak and therefore difficult to isolate and monitor, but they are an opportunity to potentially detect these P waves before S waves come. So we can do those things like stopping trains, shutting down gas lines, and eventually saving lives. Again, this suffers from a similar problem to the other one. They're very hard to monitor, and therefore, these sensing systems might not work very well. Signals are small compared to the background noise, so human activity can create electrical interference. And often, this interference is so strong that it will cause lots of false positives and false negatives. Research is continuing, but results are mixed, particularly because of these false positives, which are earthquakes that are detected but not actually happening, and false negatives, earthquakes that we aren't able to detect, which could be disastrous for human lives. One way that we are doing this electrical sensing is with fiber-optic cables. These fiber-optic cables are usually used to carry internet data as light underneath the ocean floor very quickly. The same fibers can sense vibrations. The technique is called distributed acoustic sensing. We send laser pulses down a cable, and when tiny vibrations happen, it changes the slight reflections of this cable, of this laser, meaning that when it comes back to another sensor location or comes back to the original laser location, it can reveal the vibrations. And if the laser isn't exactly where it was intended to be, then the cable is moving. This becomes very powerful because it can sense earthquakes over thousands of miles. No hardware needs to be buried because we already have these fiber optic cables under the ground. And we're using this existing infrastructure, which means that cost is low, despite being an entirely new technology. This can work in cities, along highways, under oceans, and in all sorts of places. This is particularly valuable under the oceans, since that's where we already have many fiber optic cables. And earthquakes under the oceans can be some of the most devastating, because they can cause massive tsunamis. They come to the shore, and hit our big cities along coastlines. Traditional sensors are currently sparse in oceans, meaning that this will massively improve this ocean earthquake detection. The challenges of fiber optic sensing, though, is that it generates massive amounts of data. Just one of these cables, it can come and it can have slight vibrations, and it'll show you that there's something along this piece of land, this line. But unfortunately, we're not going to be able to know exactly where. So you have to have kind of a grid pattern, a series. And then you can use, based on those lines, if this one has vibration and this other one going the opposite direction has vibration, you can directly detect where exactly that's going to be. Again, these are also sensitive to traffic, weather, and human activity, meaning that if we have a boat pass over a line, that might create a similar vibration to an earthquake, potentially creating a false positive. Distinguishing these earthquakes from noise, like those boats and like other things, can be very difficult. It is, again, one of the biggest limitations of this sensing. Another type of sensing is quantum sensors. These are called atom interferometers, and they measure the acceleration of a single atom very, very precisely. What it means is that they can detect tiny gravity changes. Earthquakes slightly redistribute the mass in an atom. And so if the atom changes in one way, the pull of gravity might increase slightly. And this atom interferometer can measure that. If the earthquake happens a different way, and the atom shakes a little bit different, mass might be now farther from the Earth, the gravity will slightly decrease, and we'll be able to measure that. These changes may be detectable before S waves arrive, meaning that we'll be able to do all of the things that could help save people's lives. This is one of the least promising and most in development of these technologies. It's extremely expensive and still very new. But again, for all of these, noise is the biggest enemy. In fact, Earth has a natural slight vibration because of what Earth is. And we're just adding to that with traffic, waves, and machines that we have in the oceans and on land that are causing problems. Physics alone isn't enough, though. Sensors are providing raw data to our computers, but this data has to be interpreted. Again, it's going to cause many false alarms, many missed signals. An accurate detection requires smart algorithms that can interpret this direct data, these specific vibrations that we're detecting, and tell you where, when, how an earthquake is happening. This creates plenty of opportunities for computer engineers and computer scientists to create algorithms to solve this problem. One great way to do it is to train AIs to do it, to detect the type of patterns that come when an earthquake is happening versus when it's just noise. Or you can use multiple sensor types. Then AI can identify patterns in the relationship between your fiber optic sensors and your traditional seismometers. All of this can be combined to create much more effective results. Systems will improve with experience, so we are only going to get better and better earthquake detection as time goes on. The physics and the sensor detection, the sensor technologies, are just constraints on how we can measure and how we can learn about earthquakes. Early warning systems already operate in many regions. Alerts are automated and extremely fast, and this effectiveness can be large depending on how dense the sensors are. Unfortunately, the ability to install many sensors in an area is dependent on that area's financial situation. Richer areas in big cities have the opportunity to make many sensors. Tokyo has very strong earthquake sensing technology that can identify it almost instantly and alert people. Therefore, access is very uneven. Unfortunately, earthquakes are a global hazard. So if an earthquake happens thousands of miles from somewhere, it can still have impacts, specifically with tsunamis. Many high-risk regions lack sensors, and so those who might not be able to afford these kind of things are dying, even when we have the technology to solve the problem, and even when this technology has so much potential to be able to solve the problem in the future. Using existing infrastructure helps, like these fiber-optic cables underground, but they're not perfect. And these fiber-optic cables aren't everywhere, because the installation of the cables has also been poor in some regions because of that financial situation as well. In the future, we can expect different sensor networks, denser sensor networks, and more use of all of these technologies to help us solve the earthquake issue. We're going to have improved algorithms with different scientists and different AI models doing things. We're going to get much faster, much more reliable alerts. We're still not going to have prediction. We're not going to be able to know days, months, weeks in the future, but we're going to have better preparedness. We can't stop earthquakes. We can't eliminate damage, but we can reduce harm. Even 5 to 10 seconds save lives. And this automated system, and the potential for automated system, can react much quicker than humans. Our preparedness can reduce panic, and small warnings can make a huge difference. Earthquakes are always going to happen, but the planet whispers before it shakes. And learning to listen to those sounds can change outcomes and make a bigger difference in the world.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.